You are watching session number 1 of the chapter, the D and F block elements. In this session, I am going to discuss about some periodic trends and physical properties of D block elements. Before moving with the actual concepts, you need to know the position of elements in the modern periodic table. Let me discuss about that. If you observe modern periodic table, we have symbols for elements. Some are metals, some are non-metals, and some are metalloids also. As we know, totally we have 18 groups and 7 periods in the modern periodic table, and first group and second group we call it as S block elements. And if you consider the group from 13 to 18, boron family, carbon family, nitrogen family, oxygen family, fluorine family, and noble gases, these belongs to P block elements. And we have some elements in between S and P, that is from group number 3 to group number 12, and these elements are nothing but D block elements. And we have two different rows, and these two belongs to F block elements here. So now we are going to talk about the elements which belongs to group number 3 to group number 12, and these all are D block elements, and these two rows what we are observing, and these are nothing but the F block elements. We are going to talk about these two in this chapter. So here we have D block elements in the middle of the modern periodic table, and then the question arises, what is the definition of D block elements? While defining S and P block elements, what is the main concept is, in S block elements we have partially filled S atomic orbital, isn't it? Whereas in case of P block element we have partially filled P atomic orbital. Similarly, while talking about D block elements, we have partially filled D atomic orbitals. The elements which contains partially filled D atomic orbitals, we call it as the D block elements. One more way you can define, whereas whenever you go on adding one electron in the valence shell of elements, here in case of D block elements we are going to add in n-1 D atomic orbital. So the elements where added electron enters into n-1 D atomic orbitals, we call it as D block elements. Remember, n-1 D atomic orbitals, the added electron enters into these elements, that's why we call it as D block elements. As we know, the position of D block elements is in the middle, or I can say that is in between S and P block elements. D block elements are also called transition elements, isn't it? Similarly, we know the F block elements are called inner transition elements. So the question arises, why we have the name as transition elements or transition metals for D block elements? The reason behind that is, if you observe the properties of D block elements, physical properties as well as the chemical properties, the properties are intermediate between S block elements and P block elements. I repeat, the properties of D block elements are intermediate between S block elements and P block elements. Because of this reason, the D block elements are called transition elements or transition metals. We know that the left portion of the modern periodic table contains metals, whereas the right portion of the modern periodic table usually contains non-metals, and in the center we have transition elements, and they are metals, I can say. So now this is the position of the elements in the modern periodic table we should know, and as I mentioned, from group number 3 to group number 12 we need to observe here. So here, if you observe the electronic configuration of the element scandium, we have 3d1 and 4s2, and similarly here the 4d atomic orbital is going to be involved, and in this series 5d atomic orbital, and in this series 6d atomic orbitals. So d block elements are classified into 4 different rows or 4 different series, and they are 3d series, 4d series, 5d series and 6d series. So the elements scandium here we have, and yttrium we have, hafnium we have, rutherfordium we have. So 3d, 4d, 5d and 6d are the series or the periods or rows we are going to talk about the transition elements. And for our syllabus we have only 3d series, means we need to talk about the elements from scandium to zinc. So you should know the names as well as symbols as well as atomic number of elements from scandium to zinc. We'll check out what are these elements and the symbols. SC scandium, the atomic number is 21. Ti stands for titanium, V vanadium, Cr chromium, Mn manganese, Fe iron, Co cobalt, Ni nickel, Cu copper, Zn zinc. So these are the elements which belongs to 3d series of transition elements from scandium to zinc. So you need to know these elements in the serial wise. So now I am going to talk about what would be the electronic configuration of d block elements, and in particular what about the electronic configuration of these elements which belongs to 3d series. So the electronic configuration, the general electronic configuration of d block element is, as we know, general electronic configuration we consider nearest to noble gas for that one. So noble gas, as I mentioned, the added electron enters into n minus d atomic orbitals. So n minus d and 1 to 10, ns 1 to 2 I can write. So this is the general electronic configuration of transition elements. And if we need to talk about valence shell electronic configuration of transition elements, and we need to write only n minus 1d 1 to 10 and ns 1 to 2. We need to skip this noble gas, near the nearest noble gas we consider. So we know that when d is the atomic orbital and s is the atomic orbital, the maximum number of electrons can be filled in s atomic orbital is 2, and whereas the maximum number of electrons can be filled in d atomic orbital is 10. Therefore 1 to 10 and 1 to 2. So it ranges the number of filling of electrons here. So n is the one quantum number and n minus 1 is the quantum number. So if you consider 4 as the quantum number, 4s atomic orbital if you consider, and this would be 1 less than that of that, and I can consider 3d. Therefore the added electron enters into n minus 1d atomic orbital. Therefore the elements where the added electron enters into n minus 1d atomic orbital, these elements we call it as d block elements or transition elements. So now this is the general electronic configuration of transition elements, and I told you the elements which belongs to 3d series. And here now you observe the last element in the 3d series. What is that? Zinc we have here. In the next series we have CD, stands for cadmium. In the next we have Hg, stands for mercury. So zinc, cadmium and mercury. And the point what I am going to say here is zinc, cadmium and mercury, they are not transition elements, they are not d block elements. And the question arises, why these zinc, cadmium and mercury, they are not d block elements? As I mentioned, d block elements must contain partially filled atomic orbitals. So if you consider the d atomic orbital, so that should range from 1 to 9, or partially filled, not completely filled or completely empty. Okay, so partially filled atomic orbitals. Whereas since the atomic number of zinc is 30 and cadmium is 48 and mercury is 80, so zinc, cadmium, mercury contains d atomic orbitals which is completely filled. I repeat, these three elements has completely filled d atomic orbitals. Since these elements has completely filled d atomic orbitals, therefore these three elements are not considered as d block elements. And then question arises, if they are not d block elements, and why we have placed these elements in the d block elements, isn't it? So zinc, cadmium, mercury are not considered as the d block element, even though we have placed in the d block elements list itself here. And the reason behind that, if you consider the sum properties of zinc and if you consider the properties of remaining transition elements, they are almost similar. Similarly, if you consider the properties of cadmium and mercury, they have some properties which are similar to the properties of transition elements. Since some properties of zinc, cadmium, mercury are similar to the properties of other transition elements, even though it has completely filled atomic orbitals, we placed in transition elements. Try to know about that one. So zinc, cadmium, mercury, they have completely filled d atomic orbitals. This is the general electronic configuration I mentioned, and now we'll see what about the electronic configuration from the elements from scandium to zinc. So let me discuss about that. So atomic number 21. So atomic number 21, and we know that is scandium, right? And 22, that is titanium. 23 vanadium, the symbol is V. And 24 chromium, Cr. 25 is manganese, Mn. 26 is iron, Fe. 27 is cobalt. 28 is nickel. 29 is copper, and the last element in the 3D series 30, that is zinc. So the first column I mentioned the atomic number of 3D series, and these are the elements from scandium to zinc. So now we will see what about the electronic configuration of these individual elements. So now see, scandium I am going to consider, the atomic number is 21. In atom, number of protons is always equals to number of electrons. Remember, number of protons is always equals to number of electrons in atom only, whereas in case of ion, that depends whether the atom has lost electrons or gained electrons. So atomic number of scandium is 21. Atomic number is 21, therefore I can say number of protons is also 21. Since it is atom, therefore the number of electrons is as same as the atomic number, that is 21. So the electrons present in scandium is 21. So the distribution of electrons in the different atomic orbitals, we call it as electronic configuration. So now 18 electrons has to be distributed in atomic orbitals by following some rules or some principles. They are Hund's rule we need to follow, Pauli's exclusion principle we need to follow, Aufbau principle, and extra stability rule also, and N plus L rule also we are supposed to follow. So scandium we have, so we can write the electronic configuration by starting 1s2, 2s2 like that. It will be quite lengthy, so therefore as I mentioned, we can consider the nearest noble gas for that one. So if you observe the nearest noble gas for these elements, the nearest noble gas is argon, isn't it? So argon, the atomic number is 18. So what I am going to consider here is the argon. I will consider that is the nearest noble gas for these transition elements. So now try to know that one. Since these are all belongs to 3D series, so therefore the electrons enter into, the added electrons enter into n-1d atomic orbital. This is the 3D series. And the one more I can write here 4s, because n-1d we have, and n will be the quantum number of s atomic orbital. 3d and 4s we are going to consider. In general, remember, for the elements which belongs to 3D series, 3d and 4s are the atomic orbitals we need to remember. And 18 electrons we have, so totally 21, we have 18. So now we need to distribute 3 electrons here. So 2 electrons are present in s atomic orbital according to n plus l rule, and now we have 1 electron, therefore I am supposed to write here 3d1. So the added electron has entered into this atomic orbital, that is 3d1. So 1 electrons we have in d atomic orbital and 2 electrons we have in s atomic orbital. In short, I can say the electronic configuration of scandium is argon 3d1 and 4s2. This is the electronic configuration of scandium. Similarly, we look over the second one, that is titanium, argon, the nearest noble gas, and we have the two atomic orbitals, one is 3d and one is 4s. So 18 we have, and then we need to consider 2, and here I need to consider 2. 18 plus 2 plus 2, you are going to get a 22. That will be the atomic number of argon. That is nothing but titanium electronic configuration. For vanadium, I can consider argon. And now we can write it directly. I hope you understood the concept where how the d orbital is going to be filled. So 3d3 we have. Whereas in case of chromium, and I am going to write the electronic configuration, that is Ar, and here I am going to consider that is 3d4, and here 4s2. So this is the electronic configuration of a chromium what I have written. But as I mentioned, we need to follow some fundamental principle while writing the electronic configuration. And one rule here I am going to apply, and that we call it as extra stability rule. So what is that extra stability rule is? The rule says that half filled atomic orbital and completely filled atomic orbitals are stable. I repeat, half filled atomic orbitals and completely filled atomic orbitals are stable. So now if you consider that 3d in case of chromium, so I have written what is that, the number of electrons to be filled in a d atomic orbital is 4, but here this 3d4 is nearer to what is that 3d5, which is half filled atomic orbital. We know that one, the completely filled or maximum number of electrons can be filled in a d atomic orbital is 10. Then half filled means half of 10, that will be 5. Therefore here 5, if we write a 3d5, that will be quite stable. So what happens here? We have a 4s2. So one electron has to be written or shifted from 4s to 3d here, and therefore I need to write here 3d5 and I need to write a 4s1 because of extra stability rule. And why I have written 3d5? Because 3d5, this is the half filled atomic orbital and it is quite stable. And we know that when all the atoms in the modern periodic table, they try to be stable by attaining the very less amount of energy. Therefore 3d5 we have, and 4s1 and 4s1, one electron we have, that is also half filled atomic orbital. Because of the rule called extra stability rule, the electronic configuration of chromium is not 3d4 4s2, the electronic configuration of chromium is 3d5 and 4s1. Know this concept. Next I am going to move with that one. Manganese atomic number is 25. So therefore what I am supposed to write? Argon. And here I hope you can mention one electron is to be added here. So 3d5 and 4s2 I am going to write here. 3d5, half a filled atomic orbital, quite stable, and one electron here I am going to consider, that will be 4s2. So now iron atomic number is 26. So 26 electrons has to be distributed, 18 we have here, and here we have a 3d and 4s, and now I hope we can guess this 3d6 and 4s2 we are supposed to write. And in case of cobalt, the atomic number is 27, argon we have, and 3d7 and 4s2. Similarly for the nickel, atomic number 28, argon 3d8 and 4s2 I can consider. For the copper, the atomic number is 29, and argon I have, and 3d9 and 4s2 if you write. And I hope now we can guess this is the wrong electronic configuration what I have written. Why? Extra stability rule. If it is 3d10, that is quite stable, isn't it? We have a 3d9, almost nearer to 3d10. Therefore one electron from S is going to be shifted to 3d here. So the right electronic configuration of chromium is, what is that? Copper is 3d10 and 4s1. And for the zinc, the electronic configuration is argon, and we have a 3d10 and 4s2. So this is how we can write the electronic configuration from the element scandium to zinc. But try to know the electronic configuration of this chromium is quite different, and you need to remember, and copper is also quite different, you need to remember. Whereas chromium, it obeys the extra stability rule by attaining half-filled atomic orbital, whereas in case of copper it obeys extra stability rule by attaining completely filled atomic orbitals, since half-filled and completely filled atomic orbitals are quite stable. So you need to remember these electronic configuration that helps us later to explain the properties like a magnetic property, electrical property, etc. So try to remember the electronic configuration of chromium and electronic configuration of copper. So now if you observe the electronic configuration of these elements, and one can guess that one, in the case of zinc we have completely filled atomic orbital. This is the reason. Similarly, if you write the electronic configuration of cadmium, 4s10 5s2 we have. For mercury, here we have 5d10 and 6s2. So all these three have completely filled d atomic orbitals, therefore they are not considered as transition elements, even though they are placed in the d block elements, because these properties are similar to the properties of other d block elements. That is all about the position of elements in the modern periodic table of d and f block elements you should know, and you need to remember the electronic configuration of that. So don't forget the position. Remember, we have the elements from scandium to zinc in the horizontal fashion in the modern periodic table, that too in the middle of the modern periodic table. Try to know the position of zirconium. Later I am going to use that one, zirconium, okay, Zr, and hafnium, that is Hf, and try to know cadmium, that is Cd, and mercury, that is Hg we have. And these two are f block elements. Later we are going to talk about f block elements, that is about the electronic configuration of d block elements. Now we'll see what about the physical properties of transition metals. The first physical property what I mentioned here is a metallic property. So what are the characteristics of metals? As we know, metals are hard solids, they are lustrous, means shining property it has, they are good conductors of heat and electricity, they are malleable, they are ductile, they are sonorous. These are the general characteristics of metals. What is the main property that makes an element to show metallic behavior? The main reason for this metallic behavior is metals have tendency to lose electrons. Since the transition elements have capacity to lose electrons to form cation, therefore these elements has the metallic character, I can say. The next physical property, as I mentioned, the melting point increases up to d5 configuration and then decreases. So we'll see that one, how the melting point is going to be related to d block elements. Try to know, melting point of an element depends on the kind of force present in between constituent elements. As we know, the transition elements are metals, the kind of force between the constituent particles is metallic bonding or metallic kind of a force you can say. So now if you observe the kind of electronic configuration what I mentioned, so for scandium we have a d1 configuration, for titanium we have a d2, d3 and d5 configuration we have. So what I am going to say here is the melting point increases from d1 configuration to d5 configuration. Why the melting point increases from d1 to d5? The reason behind that is, now as we know that one, d atomic orbital, so in a d atomic orbital we have one unpaired electron, whereas in case of d2 we have two unpaired electrons. Here we have three unpaired electrons, and here we have five unpaired electrons, here we have five unpaired electrons. So when you move from scandium to manganese, from initial 3D series to middle of the 3D series, the number of unpaired electrons increases, isn't it? So since the number of unpaired electrons increases, what I am going to say here is the metallic bond becomes stronger and stronger. The metallic bond depends on a number of unpaired electrons present in the d atomic orbital in this case. So since from d1 to d5 the number of unpaired electrons increases, because of that the metallic bond will become strong. Then if metallic bond becomes strong, how does the melting point increases? Try to know that one. we have to break the metallic bond and we need to supply more amount of energy for that one. Since if we supply more amount of heat energy, then we are going to break that metallic bond. Therefore, stronger the metallic bond, greater will be the energy required to break the bond. In short, I can say greater will be the melting point. Because of that reason, up to D5 configuration, the metallic bond increases. But later it is not the same. So later, that is after D5 configuration, from D5 to D10, if you move along with that one, the melting point won't increase, the melting point decreases here. And I hope you can guess why the melting point decreases. As I mentioned, melting point depends on metallic bond. Metallic bond depends on number of unpaired electrons. So now we'll check out what about the number of electrons from these. So now up to manganese, that is the D5 configuration, we know that 5 unpaired electrons we have. And now I hope you can guess how many unpaired electrons we have in a 3D6. Okay, and D6, how many unpaired electrons we have. So for your reference, I am going to write here, I am going to write the atomic orbital distribution or electronic distribution in the different atomic orbital. Iron, it is 26, 3D6 we have for D, and we need to draw the 5 atomic orbitals. Okay, so 3, 4 and 5, and for S we need to draw 1. Okay, and now we'll see 3D6 we have. So we need to fill the electrons in a D atomic orbitals. So try to know, this is a D atomic orbital, 6 has to be filled, and this is S atomic orbital, 2 has to be filled. Okay, so this is 3D, actually this is 4s. I can mention here, this is 3D and this is 4s. So now we have to distribute 6 electrons in the D atomic orbitals, and you need to follow the 2 rules. One is Pauli's exclusion principle and one more is Hund's rule. So what is Pauli's exclusion principle? Only electrons of opposite spin can be filled. So you need to fill the electrons of opposite spin only. And Hund's rule says that the pairing of electrons starts after each atomic orbitals are filled with 1 electrons. So 6 electrons we have. So 1 electron, 2, 3, 4, 5. If you consider D5 configuration and 5 electrons we have. So we have 6th electron, we are supposed to pairing starts now here. So therefore I am supposed to show here. So now you answer me how many unpaired electrons we have in case of 3D6. 1, 2, 3, 4. The 4 unpaired electrons we have. Anyhow, you know, in case of yes, I am supposed to show like this, electrons of opposite spin according to Pauli's exclusion principle. Therefore in 3D6 we have 4 unpaired electrons. Move with the next one, 3D7. For 3D7, I am supposed to write 1 more electron here. So how many electrons we have? 3 electrons we have. 3D8, we have 2 electrons. So here the number of unpaired electrons is 4, and here it is 3, and here it is 2, and here we don't have unpaired electrons. Or I can say the number of unpaired electrons after D5 configuration is going to decrease. If the number of electrons decreases, what is the meaning of that one? Metallic bond becomes weaker and weaker. When the metallic bond becomes weaker, then what I am going to say here is we need very less amount of energy to break that strong force of attraction. Therefore, the melting point is going to be decreased. So this is the concept regarding melting point. Try to know from D1 to D5 the melting point increases. After D5 configuration the melting point decreases. Up to D5 configuration melting point increases because the number of unpaired electrons increases, so that the metallic bond becomes strong. Therefore, the melting point increases. After D5 configuration the melting point decreases because the number of unpaired electrons goes on decreasing, so that the metallic bond becomes weaker and weaker. That is about the physical property related to melting point. The next, the keyword what I have written, melting point and boiling point maximum at the middle of the 3D series. So what I'm going to say here is, if you consider the elements from scandium to zinc, in the middle is nothing but for 24 and 25, that is nothing but the chromium and manganese. The melting point will be higher in the middle of the series. Do you know what is the reason behind that? I told you that one melting point depends on metallic bonding. Metallic bonding depends on unpaired electrons. Since in the middle of the 3D series the number of unpaired electrons is high or maximum. Do you know how many unpaired electrons we have? 5 unpaired electrons we have. Since the number of unpaired electrons is a maximum in the middle of the series, the metallic bond will be quite strong. Therefore, the melting point and boiling point is a maximum or high in the middle of the transitions 3D series. So the next physical property what I mentioned here is zinc, cadmium and mercury. They are soft metals and their melting point and boiling point is quite low. And we'll see what is the reason behind that. Zinc, cadmium and mercury. I hope you remember the position of these elements in the modern periodic table. Zinc belongs to 3D, then cadmium belongs to 4D and mercury belongs to 5D. They are the last elements in the respective D block elements. So these three have they have low melting point. Why? The melting point depends on metallic bond depends on unpaired electrons. We know that one zinc, mercury and cadmium contains completely filled atomic orbitals, or I can say there will be absence of unpaired electrons. So since there is absence of unpaired electrons, the metal melting point is quite low. Since the melting point is quite low, and we can say that they are soft metals, and especially mercury is a liquid metal, I can say. So because of the property that zinc, cadmium, mercury, they are soft metals with a low melting point because of absence of unpaired electrons, or I can say the completely filled atomic orbitals, or I can say weak or very weak metallic bond. Because of that reason they are considered as the soft metals. The next physical property related to melting point again is melting point of a 3D series is very less when compared to melting point of a 4D and 5D series. 3D series, 4D series, 5D series I mentioned, isn't it? So if you compare the melting point of the elements belonging to this series, the melting point of 3D series is very less when compared to 4D and 5D. What would be the reason for that one? In case of 4D series, 5D series, the number of unpaired electrons is more when compared to the number of electrons present in 3D series. Since large number of unpaired electrons we have in 4D series, 5D series, that is the reason why the melting point of 3D is less, or you can say the melting point of a 4D series, 5D series will be higher when compared to the melting point of a 3D series elements. And now why the number of unpaired electrons will be high, or you can say the melting point will be high? That depends on one more property, that is the enthalpy of atomization. Let me explain what actually enthalpy of atomization. If we have a molecule and the molecule is going to be dissociated into atoms, and we need to supply a kind of energy for that one, isn't it? So the change in enthalpy involved, enthalpy, heat content you can say, the change in enthalpy involved, so that the chemical bond is going to break and atoms are formed, and such a change in enthalpy we call it as enthalpy of atomization. Atomization, there will be formation of atoms. Due to that, the chemical bond is broken due to the enthalpy what we supply, and atoms are formed. That we call it as enthalpy of atomization. Remember, enthalpy of atomization for transition elements is quite high. When you compare the enthalpy of atomization of 3D, 4D, 5D, it goes on increasing. Why? Because enthalpy of atomization will be quite high in case of D block elements or transition elements. The reason is the same. D block elements or transition elements have large number of unpaired electrons. Since large number of unpaired electrons we see in a D block elements, therefore D block elements possesses high enthalpy of atomization. That is the one more physical property related to that, and all these are the physical properties of transition elements or D block elements you can see, and this electronic configuration is the fundamental, so that we can explain the electronic configuration or the filling of electrons in the different atomic orbitals. Try to know, you need to know Pauli's exclusion principle, Hund's rule, Aufbau principle, and one more extra stability rule, so that one can write the electronic configuration like that in a very easy manner. periodic trends involved in a d block elements I am going to discuss now. The first one I am going to talk about atomic size or ionic size, ionic radius we can say. As we know, the distance between center of the nucleus and the electron present in the valence shell, that we call it as atomic size. Down the group, atomic size increases, whereas along the period atomic size decreases. Down the group, atomic size increases because the number of shells increases, isn't it? Whereas along the period atomic size decreases. The reason behind that is number of shells remain same, but effective nuclear charge is going to be increased. So now we'll see about 3D series elements only, the elements from scandium to zinc. As we know, these elements are situated in modern periodic table in horizontal fashion. So therefore what I am going to say here is, in general the atomic size of 3D series elements are going to decrease because they are arranged in horizontal fashion, or I can say number of shells remain same but the effective nuclear charge is going to increase. But this is not linearly decrease. We have some exception or changes we are going to observe. What is that? Observe here, I have mentioned the elements from scandium to zinc. Atomic size or ionic size decreases from scandium to chromium. So if you move along scandium to chromium, atomic size is going to decrease. What is the reason behind that? The reason is, from scandium to chromium, even though the number of shells remain same, but the effective nuclear charge increases. I repeat the word, effective nuclear charge. The charge possessed by the nucleus we call it as effective nuclear charge, because since the number of shells remain same, so when we move from scandium to chromium, number of electrons increases, because number of electrons are going to add in the 3D atomic orbital, isn't it? So since number of shells remain same, number of electrons is going to increase, or I can say effective nuclear charge is going to increase. So because of that, there will be decrease in atomic size from scandium to chromium. But after that, if you observe, that is from chromium to copper, from chromium to copper, the atomic size is not going to decrease. They are almost the same, not exactly same, they are almost the same. Even though from chromium to copper, number of shells remains same, as well as effective nuclear charge increases. So since effective nuclear charge increases, but in general we think that the atomic size has to decrease, but in this case the atomic size will almost remain same. The reason behind that is, the increase in effective nuclear charge is balanced by or compensated by shielding effect or screening effect. The word what I used is screening effect or shielding effect. So what happens? Number of shells remain same, then the number of electrons increases, as a result effective nuclear charge also increases. So what happens? There will be a force of attraction between center of the nucleus, because in the center of the nucleus we have protons and electrons used to revolve around the atomic orbital. So isn't it? So because of that, there will be a force of attraction between a positively charged nucleus and negatively charged electron. Since the number of electrons goes on increasing, effective nuclear charge increases, but we have some other electrons in between for that. So that acts as a screen that is going to shield the increase in the number of electrons, that we call it as effective nuclear charge. Because of that, the atomic size from chromium to copper, they are almost the same. What I am going to say in the very simple manner is, increase in effective nuclear charge is compensated by shielding effect or screening effect, I can say. So from scandium to chromium decreases, from chromium to copper almost the same. Whereas if you consider the zinc, okay, so atomic size of zinc will be quite larger when compared to the atomic size of copper. The reason behind that is electron cloud. Since zinc contains completely filled atomic orbital, the electron cloud of zinc will be quite large when compared to the electron cloud of copper. Therefore, the atomic size of zinc will be a little bit higher when compared to atomic size of copper. That is the periodic trend called as atomic size. Try to know in general atomic size decrease, but here some exceptions we have, and that depends on the concept called effective nuclear charge and screening or shielding effect, and based on that it is not linear. From scandium to chromium decreases, chromium to copper almost same, zinc will be quite high when compared to the preceding transition element. After this we'll move with the second periodic trend, that we call it as ionization energy or ionization enthalpy or ionization potential. Minimum amount of energy required to remove valence electron from isolated gaseous atom, we call it as ionization enthalpy, ionization energy you can say. So in this case of 3D series transition elements, ionization enthalpy increases. So try to know that one, ionization enthalpy increases in 3D series. Why the ionization enthalpy increases? Try to know, atomic size and ionization energy, they are inversely proportional to each other. If the size of an atom is quite high, then it can easily lose electron, or I can say you can easily withdraw the electron from the outermost orbit, isn't it? So since along the period atomic size decreases, then what happens? The ionization energy is going to increase, I can say. In simple, you remember atomic size and ionization energy are inversely proportional to each other. And here I am going to use some terms called first ionization energy, second ionization energy, third ionization energy. Let me explain what is the meaning of first ionization energy and second ionization energy. In general, let us assume this is the atom and the center of atom. Okay, this is and now I am going to consider one shell or one atomic orbital. Let me consider this is one electron and this is one more electron. In general, this is one very simple atomic orbital diagram where I have mentioned 2 electrons. And this is the valence shell, this is the outermost shell, and these are the valence electron. So what I am going to do here is, I will supply a certain amount of energy so that I am going to remove the valence electron, and what we term it as? We term it as ionization energy, and the valence electron I just removed, okay, and now I call it as the first ionization energy, IE1 I can say. So now this electron, I just removed that one, and we have one more electron here, and what I do, again I will supply a kind of energy so that this electron is also going to be removed, and now I call it as a second ionization energy. So this is actually the meaning of first ionization energy, second ionization energy, and inside if we have one more electron, and that also can be removed by applying a kind of energy, that we call it as third ionization energy. Second ionization energy, in simple I can say, the energy required to remove the second electron from the valence shell, that we call it as second ionization energy. So this concept you need to remember. So what I have written is, second ionization energy also increases. See, ionization energy, we just removed the valence electron. So if you try to remove the second electron, and in that case also you need high amount of energy, and from scandium to zinc, second ionization energy also increases. The reason is same, that is the atomic size is going to be decreased. And now we'll see some examples for that one. So what I have mentioned is IE2, as I mentioned, second ionization energy. Second ionization energy of chromium and copper is high. So we'll see why the second ionization energy of chromium and copper is high. As I mentioned the elements here, so chromium, do you know what is the atomic number of chromium? You need to remember the atomic numbers and electronic configuration in the serial wise from scandium to zinc. I mentioned that one. So atomic number is 24, and electronic configuration of chromium is 3d, 4s, 3d, 5 and 4s1. Chromium, it is quite stable because extra stability rule. So half filled atomic orbital is completely stable. Therefore the right electronic configuration of chromium is argon, 3d5 and 4s1. We'll see the one more. So what is that? The copper we have. Do you remember what is the atomic number of copper? 29 it is. Argon, 3d10 and 4s1 is the electronic configuration of copper and chromium. Remember, if you talk about ionization energy, again the rule has to be applied, that is extra stability rule. I repeat, half filled atomic orbitals and completely filled atomic orbitals are stable. So now if you consider what actually chromium here, okay, so what is the meaning of first ionization energy? The valence shell will be 4s, so we need to remove this electron, one electron we have, we need to remove this electron. So if you remove this electron and the energy required, we call it as first ionization energy. So after removing this electron, and now I need to consider what is that, 0, because I have removed one electron. So now second ionization energy means I have to remove the second electron, the next electron. So next electron we have 3d5. So 3d5, half filled atomic orbital. Half filled atomic orbital is quite stable according to extra stability rule. So it is difficult to remove the electron from stable atomic orbital or stable nucleus, you can say. Since 3d5 is half atomic orbital which is quite stable, of course we can remove the electron from that, but we need high amount of energy. So that's why what I am going to say is second ionization energy of chromium is high. We'll check out for the copper. So the first ionization energy, we have to remove this electron. So after this electron, we have what is that, 4s0, and we need to remove the electron from 3d10. So 3d10 completely filled atomic orbital which is quite stable. So if you want to remove the electron from this also, we need a high amount of energy. So because of that, what I'm going to say here is second ionization energy of copper is high. Try to know that one. Second ionization energy of chromium and copper is high, because in case of chromium, half filled atomic orbital we get which is quite stable, and therefore the ionization energy, particularly second ionization energy, will be high. In case of copper, completely filled atomic orbital which is quite stable, we need high amount of energy to remove the second electron from copper. So that is the meaning that second ionization energy of chromium and copper is high. We'll see some other examples. First ionization energy of chromium is low. First ionization energy of chromium. So chromium we have, what is the electronic configuration of chromium? That is 3d5 and 4s1. So first ionization energy of chromium is low. Why it is low, we'll see. First ionization energy means I have to remove this electron. So if you supply energy, I am going to remove this electron, and that we call it as ionization energy. So after removing the first electron, we are left with the electronic configuration which is stable, because half filled atomic orbital we have. So after removing the valence electron from that chromium, we are left with the stable electronic configuration, or I can say half filled atomic orbital which is quite stable. So because of that reason, the first ionization energy of chromium is low. No, that one. Some other examples. First ionization energy of zinc is high. We'll see that one. Zinc, atomic number is 30, electronic configuration argon, and 3d10 and 4s2 we have, 3d10 and 4s2. So completely filled d atomic orbital as well as this atomic orbital we have. So what I'm going to say here is first ionization energy of zinc is high, and you need to think about that. Why the first ionization energy of zinc is high? I hope you can guess. First ionization energy means out of 2 electrons you are supposed to remove the 1 electron. So yes atomic orbital, S2, that is completely filled. So completely filled atomic orbital is quite stable. Again, since here it is completely filled atomic orbital, so it is difficult to remove the 1 electron or valence electron from that one. Based on that, I can say the first ionization energy of zinc is high. Second ionization energy of zinc and second ionization energy of copper. We'll compare that and we'll analyze. So copper electronic configuration is 3d10 and 4s1, isn't it? 3d10 and 4s1. For zinc it is 3d10 and 4s2. So what I am going to say here is second ionization energy of zinc is less than second ionization energy of copper. See here, we have 4s1. First ionization energy means you have to remove this one, and we are left with 4s0. And first ionization energy means we are supposed to remove this electron, isn't it? And we are left with the 4s1, first ionization energy. But here I am going to talk about second ionization energy. See here, second ionization energy in case of copper, we have to remove the electron from 3d10. And it is completely filled atomic orbital which is quite stable. Therefore second ionization energy of copper is high. Whereas in case of zinc, second ionization energy means we have to remove the electron from 4s from one electron. We can easily remove that one. Okay, so because of that, what I am going to say, after removing one electron, we are left with 3d10. But in case of copper, we have 3d10 and we have to remove the electron from 3d10 configuration only. That is completely filled atomic orbital. It is difficult to remove. Therefore, the second ionization energy of zinc is less when compared to second ionization energy of copper. We'll compare some other examples. I'm going to consider manganese and I'm going to consider iron. Manganese atomic number 25 and the electronic configuration is 3d5 and 4s2. Iron 26, it is 3d6 and 4s2 we have, and we'll see the second ionization energy of these two. So first ionization energy means we need to remove one electron and we need to remove one electron, and I am going to remove these electrons. Okay, and we are left with the 4s1 and we are left with the 4s1. So now second ionization energy we need to think. So second ionization energy of manganese is less when compared to second ionization energy of iron. What is the reason behind that? I hope if you apply the extra stability rule, you are going to get the answer for that one. Second ionization energy. So if you remove this electron, the second electron, and we are left with 3d5 half filled atomic orbital, that is quite stable. And if you remove one electron, we have 3d6. This is neither half filled nor completely filled. It is 3d6 we have. So this 3d5 is quite stable when compared to 3d6. That's why the second ionization energy of manganese is less when compared to second ionization energy of iron. We'll consider the same elements. We'll talk about third ionization energy. So third ionization energy means we need to remove this electron also. So if you remove these two electrons, we are left with 4s0 and 4s0. So now we'll see third ionization energy. So you have to remove one electron from 3d5. You have to remove one electron from 3d6. 3d5 half filled atomic orbital. So it is difficult to remove the electron from this. Whereas in case of 3d6, this is not stable and it is very easy to remove the one electron from this. Based on that, I can say the third ionization energy of manganese is quite high when compared to third ionization energy of iron. So third ionization energy of nickel, copper, zinc, 28, 29, 30. Nickel, copper, zinc, the third ionization energy will be quite high because the oxidation state possessed by these is maximum +2. Okay, so there is no oxidation state with the +3. Okay, so based on that, I can say it is very difficult to remove the third electron from that. That's why the third ionization energy of these elements is quite high. So this is all about the second periodic trunk, that is ionization enthalpy. Remember, if you are going to talk about the second ionization enthalpy, first ionization enthalpy, you need to apply a rule called extra stability rule, and based on that you can apply n kind of examples like that, and you need to think over that. But it is mandatory to remember the atomic number, electronic configuration, and based on that only we can do some rough work and we can guess what would be the statement or final statement what we can write for second and first ionization enthalpy for comparative elements here. And now I am going to talk about oxidation state. The permanent or actual charge possessed by atom of an element, we call it as oxidation state. And oxidation state we get when the elements loses electrons and gains electron. Because of that we get the oxidation state. Remember, the transition elements have variable oxidation state. What is the oxidation state of sodium? +1. What is the oxidation state of oxygen? -2. In some case it is -1. So whereas if you consider oxidation state of transition elements, we have a large number of oxidation state. One example I will give you. If you consider manganese as an example, we have +2, +3, +4, +5, +6, +7. Totally 6 different oxidation states we have. Not only for manganese but also for all the 3D elements. Not only 3D but also all transition elements, we have variable oxidation state. Why does the transition elements possess variable oxidation state? And the reason behind that is number of unpaired electrons. As we know that one, number of unpaired electrons will be more in case of transition series. Because of that, they have the variable oxidation state. And if you compare the energy levels of 3d and 4s, they have comparable energy levels. 3d and 4s atomic orbitals, since they have comparable energy levels, because of that also the transition elements possess variable oxidation state. And now, as I mentioned, we have one such element in a 3D series. I am going to talk about 3D series only. In a 3D series, we have one such element that has a maximum or highest oxidation state, and that is manganese. And oxidation state maximum possessed by that is +7. And I will give you one example. If you consider one compound, that is KMnO4, potassium permanganate, okay, and here the oxidation state of Mn is +7. As you can calculate, oxidation state of potassium is 1, because that belongs to the first element Mn. We don't know. Oxidation state of oxygen in all compounds is -2. So what we have, -2 into 4, which is equals 0. If you calculate that, x is equals to +7 we get here. Therefore, this is the best example what I can give, where the manganese has the highest oxidation state. What is that? +7. Try to know in a 3D series only, not all transition elements. In a 3D series, the element which has highest oxidation state is manganese, and the highest oxidation state is +7. We have such element, we have one element that does not show variable oxidation state, that has only one oxidation state, and that is scandium. So the oxidation state of scandium is +3. We have only one oxidation state, we don't have more than one, that we call it as variable oxidation state. So scandium is the element which does not have variable oxidation state. Try to know, manganese has highest oxidation state +7, and scandium does not have variable oxidation state, and the oxidation state is +3. Similarly, the other elements, and they are vanadium, chromium, iron, cobalt, nickel, they have variable oxidation state, or I can say the oxidation state more than 1, and that is about the periodic trend, and that is the oxidation state. And that is about some physical properties and some periodic trends what we studied in this session. In the next session, we'll discuss about some other physical properties and chemical properties of transition elements.